I want to talk about another case of a circuit that I want to look at in a control system, look at its various pieces, and sort of talk about, can we talk about controlling such a system as a result? All right, so I'm going to want to look at this particular linearized circuit. Now, some of you might go, where did you get this circuit? And it turns out, if you're curious, this actually comes from a transconductance amplifier circuit. It's sort of a linearized model, but not surprising because all of these voltage controlled current sources really come from transconductance amplifiers. And this would actually come from a circuit that is a second order section that came from Carver-Mead originally. And it had a very interesting structure because it created it in a way that illustrates what's going on with some of the eigenvalues and allows you to sort of see that you're almost introducing positive feedback. And this term A is almost a way of saying what positive feedback are you introducing into the circuit. Okay, so let's take a look and let's analyze what we would see here, and let's think about how we approach this. First, we talk about these circuits. We have the same C, we have a constant parameter G all the way through, and as a result, I can actually write the two equations for the circuit, basically just doing KCL at V1 and KCL at V out around the C and around the C. If I'm looking at this from a control perspective, I realize that, oh, these are my state variables. Usually integrating current on a capacitor is my state variable because that's what's going to give me C dV dV out dt equals a current. It's exactly the right form with sort of this constant C term in there. Great. Well, it turns out I also have the G's in there, and so if I realize very quickly that I have sort of a natural place to define a time constant, which you can C over G, which is basically RC. G is just conductance, so it's 1 over that. And so as a result, this is what I'm going to get. Okay, nice. But here's the thing, that many times by figuring out the time constant and normalizing time by it, it allows me to simplify the problem. So in this case, I'm going to take that time, and I'm actually going to take it by tau times T1. And so I always know that I could shift stuff by tau. And in fact, if I'm looking at the original circuit, I just basically have to change a different bias current. And again, if I'm in a programmable circuits, which is really fun, I just have to program a new current. Off I go, life is good. So it makes sense to think about these things in their normalized space. Okay, great. So now if I look at the normalized space, I get these two equations here. By the way, it also does something else. It also keeps the amount of math down. It keeps it down to the fundamental spaces. And in many cases in nonlinear dynamics, you want to get it down to just what are fundamental parameters. So you should always be thinking about this. Okay, so given this structure, I can now say, my two state variables are V1 and V out. Let me just put them together here. I have my input is actually Vn over 0, because that's kind of where it's going to sit. And as a result, I get the state equation as a result. Yay, I can look at this. Cool. Now I can look at the eigenvalues for A, for the matrix A, for any parameter little a. A little bit ambiguous here, but usually we use the parameter A, so I'm trying to keep it consistent with certain notation there. But if I work my way through, I actually find that here's what my eigenvalue expression would be. And what I find is for different values of A, I'll get different ones. If A is 1, it turns out I'm going to get stable and complex roots. So it'll be stable, it'll converge to 0, but I will get some oscillatory behavior as I approach, if I were to look at the phase plane of the structure. If A is 3, what I'm now going to see is I'm going to see unstable, complex roots. And now this is going to be a case where it's going to converge away, it's going to spiral out. Now, often these kinds of structures are at the core of, say, for example, a Van der Pol oscillator or something. So I would love to see it actually expand out because that's what builds an oscillation. Okay, very cool. But let's say I'm handed this case of A equals 3 and I say, I just want to control this. And it's interesting to kind of just take these simple cases to kind of understand how complicated control problems can actually get, or just even with a simple thing, because you say, well, okay, great, let me just do a linear feedback and let's see if it works. Now, if you're looking at this closely, you're going, wait a minute, this is going to be in sort of my decay term that's kicking it around, so maybe I'm a little nervous here. Fair enough. So, but I still added into the state equation, which is what I had before, but then I noticed my U of t becomes something related to V out. That changes my matrix, it changes my lambda. You go, great. But here's a problem. This is always going to have at least one root being positive all the way through. So the reality is this kind of feedback will never stabilize the system, which is not surprising when you get the sort of real or sort of the complex kind of roots that you're going to get out of a system like this. So you need a much more complicated control structure to kind of break this dynamic. But it's kind of an interesting thing to kind of work through an example like this for a very simple control system and to see what you might actually get as a result.